Welcome and congratulations for making it all the way, almost all the way to the end of Black Hat and for joining here and listening into our talk. Let me assure you, you won't regret it because after this talk, you may look a little bit different at some of the devices you have, like your phone, your laptop, your tablets, your watches. Now, let me first ask you a question, and I want to see some hands. Who does have a device that has a webcam? Yeah, I guess majority of people, what can we do? I think most laptops, most phones have webcams. So who has actually sat in front of a computer and was wondering, am I being watched? Am I being recorded? Yeah, quite a couple of hands. And so what we're going to show you today is that this scenario is not really unrealistic, but it not necessarily there is a human on the other side watching you. Instead, it could be malware that is sitting on your computer already for a while and maybe watching you stealthily. So I'm leading the cognitive cybersecurity intelligence team at IBM Research, and I'm being joined here with two of my colleagues, Dilung Kirat and Zhiyong Chang. At IBM Research, we have a long tradition of analyzing new technologies, new threats that are being posed by these new technologies. How do these technologies emerge and what do they mean for the cyber threat landscape? When we look back at what happened over the last decades, every shift of technology has impacted cybersecurity quite a bit. In the PC era, viruses, worms came up, and they stayed till today. Later on, in the web era, we had cross-site scripting, cross-site request forgery that was affecting many websites. Now, more recently, we have seen a big push with AI. AI becoming very powerful, but also becoming highly accessible to people. In fact, you can download lots of AI libraries that can do many great things today. Open source available. So we can call this a democratization of AI. Everybody pretty much having access to AI. And indeed, we've seen many amazing things that come out of AI, people using AI and create great tools. However, AI can be used for different purposes, good purposes, but also less good purposes. And in fact, bad guys, cyber criminals out there are studying up on AI and use it for their advantage and weaponize it. So we've seen very recently a number of examples of AI is being used to create new forms of attacks, making them stronger, harder, more evasive. For example, we've seen how researchers have shown that you can create emails with AI that evades existing spam filters, or how they are mining social networks to find very targeted people that the spam campaign should go after. Or last year, Black Hat, we've seen Hiram Anderson talk about how he's using genetic algorithms and reinforcement learning to create ways of how the malware can mutate existing malware and then bypass antivirus filters. Or even, AI making attacks very creative, changing things that the human attackers wouldn't have anticipated. We've seen some examples also last year where there has been intrusion SQL injections where the AI hasn't even understood what SQL is. We call these types of attacks AI-aided attacks. Now, what we're going to show you today and talk about today is a different form that we call AI-embedded attacks. So different to what we've seen where you use AI to kind of craft different types of malware or run some type of campaigns with the AI. Here, the AI is really deeply embedded in a piece of malware. Almost, think of like bringing the brain of the cyber criminal into the malware itself and take decisions. So what we're going to show you is really how attackers can take AI readily available for them and create new forms of attacks. In particular, we're looking at something that is becoming extremely evasive and extremely stealthy. So the AI is really being used to create a way to hide the presence of the malware and to evade from detection. So in this context, let me briefly talk about the evolution of evasive malware. And this is really, a cat and mouse game. We know this very well in the security domain. We have attackers or malware creators that wrote some piece of malware and they realized antivirus systems are picking up on it. They have signatures to find our malware. Obviously, they went on, they then did some obfuscation. We've seen how they mutated payload, polymorphic and metamorphic malware came out, which then led to the security industry to look at program analysis, trying to de-obfuscate what's going on and understand there are some bad things in that payload. Attackers went on adding encryption, packers, to basically hide the malicious payload. Security industry, on the other hand, then, okay, let's take a dynamic analysis, malware sandboxes, run these things to see what's going on. Malware writers came back, we're gonna check for malware sandboxes. Are there any processes? Are there VMs where we were executed? Then we're not gonna execute. And so on and so forth. We had anti-malware, anti-sandboxing technologies then by the security industry, all the way to attackers really creating very crafted, targeted attacks and malware that only executes under very specific conditions and then only show their malicious intent. Now, what's the next step? Because when we look at this, we realize in all cases, we have some clues for the malware analyst in this malware. If you look at this manually line by line, you see a couple of interesting things. There's always a key. It may be physically present in the malware, or it may be received via a command and control network. And then there are these checks. So you can still very well see that if you're really analyzing the malware, that there is some malicious things going on, there is some intent. But what if there is no key? What if there is only a key maker embedded? And that key maker can decide when to generate a key and under what conditions a key can be generated. So we developed a proof of concept, and we call it DeepLocker. We developed this to demonstrate how easily today attackers can take AI and can create such key makers that are very hard, if not impossible, to reverse engineer. So I'm going to hand it over to my colleague, Jiyoung, to take you through a demo of how DeepLocker can work in practice.
All right, thank you, Mark. So some of you who came to the room early and we are busy on the stage and might be curious, what are these guys doing with the camera, laptop? As you can expect, we are going to show a quick demo. And the demo is about to demonstrate what the cyber criminals maybe can do with the AI and what kind of the targeted and evasive attack may be achieved. So specifically for this demo, and we are going to show how the DeepLocker can be widely distributed while remaining stealthy. So from the last year, you may remember there was CCleaner incident. It was quite sad story. So CCleaner is one of the popular Windows utility program that is supposed to clean up your Windows registries and file, which is not necessary. But unfortunately, the problem was that the CCleaner, their software development pipelines got compromised, such that their register-made download server started hosting the CCleaner with malicious code embedded. And the problem was that the malicious version of CCleaner had been downloaded by more than 2 million users, which is quite a significant number. So for the demonstration purpose, we designed a program called the Talk, which is about video conferencing application for the demonstration purpose. So Chris, maybe we can switch to the camera. To input, to camera. Yeah. Is it too dark? Is it? Okay, maybe too dark. Let me just increase a little bit. As you can see, there is a laptop And as a user, I'm going to go ahead and download to start using the program video conferencing application called Talk. Okay, there is application download. I'm going to download the program, save to my computer. Okay, I should have my program at the download port. Okay, now we have the program. Of course, whenever there is new updates comes in, people go to download the new binary, and always there is new user comes in, start using that binary program. And this happened many, many times. So I'm going to start using this program, and I'm going to run it. So program is running. As you see, this is program called Talk, and which is video conferencing application. Nothing suspicious happened. Everything looks normal. So at this moment, what may not be obvious is that actually the malicious code inside this program. And it is specifically tailored for the one specific person. So for this demo, so I'm going to invite one person from the audience for the demo, and who is our speaker liaison, Bob. And Bob, can you please come onto the stage? So Bob is
Applause
one
for
of our...
Bob, please.
Okay. So as a normal user, okay, you probably start trying to using the program. And okay, maybe you'll get a little bit of different angle. Come on. Yeah. Oh, what happened? So you just see, maybe I have to zoom in a little bit. So you see the famous WannaCry ransomware. It just popped up. So what just happened is that the video, the webcam of this camera just did see the Bob's face, and it released the malicious payload, which was WannaCry in this case. So what happened was that we specifically trained this program to recognize specific target. For our demo, the Bob was volunteered, and we used Bob's face as a specific target. And this program is actively looking for a specific person, and looking for a specific person to release the program. Chris, can you switch on to the slide deck? Thank you. So as you can demonstrate, the cyber criminals can embed any kind of the malicious software into any kind of benign program using AI technique. So what it makes extremely dangerous is that, as you can see, it may infect millions of people, but it may reveal the malicious intent only at a specific target. So it becomes really stealthy. It may be evading all the different sandboxing or static analysis technique. So it makes it extremely hard to understand and decode and analyze the program. Then at this moment, probably you have in mind, okay, how this can be done. And from now on, I'm going to invite the Dilung to go through what's really happening inside of the DeepLocker AI factory.
All right. I hope you enjoyed the demo. So far we can see that we're using AI, or the attacker is using AI to detect or recognize the target. But the story is not only that. The story is that it's also concealing what it's targeting. And I'm going to focus on that part, the scaling part of the target. So if we look into, from the high level, what is a targeted attack, right? It's simply a very simplistic if condition where it asks this question, which is this system is a target? And if the answer is no, the program is going to end. And if the target is yes, it's going to execute its attack. So we can see that, for example, in the Stuxnet, if you look into the code, you'll see that it's actually checking for the presence of certain application. In this case, step 7 application. And if it sees that application, then only it's going to execute its attack. So for any targeted attack to be very, very stealthy, there are two components that it really wants to hide. The first one is the target specifics about the target, like what it's targeting. And the second is the actual attack. What's the real goal of the attack? And we see this logic that no matter where this attack is running, it must ask this question before it steps further, that is it a target? And we can see that. And the problem is, if there is a malware analyst looking into this malware, it will see that it's asking the question, and then they can simply pass that question that is basically pass that if condition and directly jump into the actual malware code and run in a sandbox and see what exactly it's trying to do. But we realize that this very simplistic form of if this, then that kind of construct can be actually transformed into a very convoluted and very complicated logic of decision logic using deep neural network. So what I mean by that is the attacker is using deep neural network to decide whether to attack or not. And then the problem for the defender is that looking at this AI model, it's going to be very, very difficult to figure out what it's targeting and what is the right target, and figure out the actual malicious code. So why is that the case? To understand a little bit more into that, let's quickly look into what exactly deep neural network is. So it's basically, from the very high level, it's basically we have 3 layers: the input layer, hidden layer, and output layer. Input layer probably is getting some sort of sequence of pixels that represents a cat, for example. The hidden layer is doing its magic and producing some probabilistic score that whether it's a cat or dog or something else. And inside the hidden layer, there are multiple layers of computational nodes that are using the input and transferring the value to the output. There are also some linear and nonlinear layers that's making this network more complex and is able to capture and learn a lot of complex concept of the input. This form of neural network is actually quite old, dating back to 60s. But the recent iteration of the neural network, which we call the deep convolutional neural network, is actually introducing this new type of neuron called the convolutional neuron that is able to learn about new filters and understand high-level concepts of the input, such as painting a style of Van Gogh or something like that. And that's great. That's really great. And we have seen great results with this new form of neural networks. But what is interesting about these deep neural networks is that they are very, very complex and deep to analyze and understand what's happening. For example, this is a LXNet, which was one of the very first deep neural network that was able to produce really good result. It has 8 layers and already 600,000 plus neurons and 60 million plus parameters. So if somebody wants to know what's happening inside, it's going to be very difficult. And in fact, researchers, the whole AI community, have been trying to understand and interpret what's happening inside, how they're encoding the knowledge, and how the deeper neural network AI models are encoding different aspects of the input parameters. Since it's difficult, the attacker can actually use that fact that it's very difficult to understand and analyze these logics and use that to conceal the information of the target. They encode their logic of target detection inside the deep neural network. And that's exactly what the DeepLocker is doing here. And since we are using deep neural network, it can actually consume different types of variety of target attributes. For example, in this particular demo, we saw that it was looking at the video and trying to capture the face, but it doesn't have to stop there. It can look for audio, can try to recognize some voice recognition. It can look for a software environment, such as in this case of Stuxnet. It can look for more advanced user behavior and attack certain types of user, maybe a manager or developer or something like that. It can look for geolocation to pinpoint its target. It can even look for sensors. And what I mean by the sensor is that, for example, we all have cameras in our phones, and these sensors during its manufacturing process, there are non-linearity in their pixels. All the pixels are not the same. They have different sensitivity to light, and you can actually, turns out, extract those very specific distribution of this non-linearity in your sensor from your maybe pictures that you post in your social media, and then use that, encode that into DNN model and detect that specific phone and only target that. Of course, using all these sensors and availability, geolocation, and all that, you can even derive a very high-level physical environment clue using all the sensors and whatever the attributes you can access. So how would somebody, if they want to implement it, how would they go about it? So attacker, usually in the case of face recognition, there are DNN that are trained to recognize face and generate some kind of a feature vector of the face. That's a facial feature vector in some high dimensional space. And if you want to detect the target, a naive way would be to implement some kind of a template matching. And what that is basically you have a target template. That's the feature vector of the target. And when you grab the input and generate a new feature vector and you compare with the template, basically compute some kind of a distance. And if the threshold is lower than what you expect, you detect that it's a target. However, the template matching requires a template to match, and that's the problem. Because so you have to include this reference face inside your malware, right? The attacker has to include this template, and that means you are giving away some information about the target. It's not concealing the information about the target. So we realized that instead of training the DNN to spit out this feature vector for the facial feature vector, you can actually train the DNN to generate a unique key, a deterministic key that is only generated when it sees the target. So with this, the attacker will be able to completely conceal what the target is because it's all inside the DNN model, which is very difficult to decipher. And using this key, it can also encrypt the actual payload, which is the real bad thing, and hide it completely in the payload. So from to overview that, so basically, if a targeted the target generation, first there are two stages. First, you do the concealment, that is, you generate the malware. For that, the attacker has to first figure out, what are the attributes he or she wants to use to target the attack, and then he has to select some secret key and then train the DNN model so that it generates the key when it sees those particular attributes. And using that key, it can encrypt the actual payload and generate a concealed payload. And in the unlocking phase, the DNN will look for these attributes, and if and only if it sees these attributes, it recovers the key and converts the concealed payload into the real payload and executes it only at the target. So if you see that the attacker only has to transmit two things from this process, that's the DNN model and the concealed target. So the only two things. So there is no key to debug and uncover from the distribution of the malware. And it will be very, very difficult for any analyst, manual analyst, to find out the key because it's hidden in the AI model, the target. Either you need to know the target, which is already a secret, and until you don't know the target, you don't have the key. And if you don't have the key, you don't know what the payload is. So let's look at a little bit into the key generation. For the case of face detection, so usually there is the DNN model that generates some kind of feature vector that as I mentioned before. And then one naive way of converting this to key would be to do some sort of quick bucketization, right? If it's to 0 to 1 and creating a bits for your key. If it's 0.9, it converts to 1. If it's 0.0 or 1, it converts to 0, and so forth and so forth. But turns out if you use this kind of bucketization, the key is very unstable. That is, even for the same person's face, the feature vectors there are enough randomness that 1 or 2 bits is going to be flipped, and then your key is not going to be the same, and you'll not be able to properly generate the attack. And this is because these high dimensional feature vectors are close in the higher dimensional space, but the individual dimensions may have some variation there. So we realized that instead of using the bucketization, it can also be replaced by another DNN model. So basically what you do is you select some random key and train the key generation model, what we call the key generation model, to spit out that specific key whenever it sees these parameters or the facial feature vectors. And this key generation model is a type of multi-class classification model where the outputs nodes represent a bit or class. And you train such that, for example, if we select a key that is 01101, and all the our ground truth for the input target would be class 2 and class 3 and class 5, and it won't belong to class 1 and class 4. So that would be our ground truth, and we train the key generation model so that whenever it sees the target, the first stage of the DNN produces the corresponding feature vectors, and that will be mapped into the very specific deterministic key that we use to encrypt the payload. So we did some analysis with this approach of key generation model. So, we use publicly available data set, that is the labels faces in public. And what we're seeing here is the performance of this key generation model. So we have the precision and recall. Precision measures how precise the model is, and then the recall represents how complete it is. For example, if the generation model generates 10 valid keys, and it turns out those 10 valid keys are generated from real targets, so that's we have 100% precision. But if there are 20 input target pictures, but only 10 was able to generate the real key, then we have only 20%, 50% recall. So if you look at the graph, we see that it's very, very precise. Precision is 100% when you have enough training. So what that means is whenever it generates a key, it is the target. But the recall is not 100%, but that means maybe some images may not convert into real key, but that's probably not going to be a problem for an attacker, because the whole goal of the targeted attack is, sacrifice. They sacrifice the target space, but try to be very stealthy and keep their code away from the defender. So finally, with this approach of AI powered concealment, what the attacker is able to do is have 3 layers of concealment for their attack. The first one is that the target class concealment. And what I mean by that is, when looking at the key generation model, you won't be able to tell what it is targeting, what class of target it is. Is it targeting an individual? Is it targeting an organization? Or maybe is it looking for something very obscure object that is only available in the target's environment? Next layer of concealment is the target instance concealment. That is, even if we guess that maybe it's a face that it's looking for, it doesn't tell us what individual's face it's looking for, what's exactly the key that is looking for, what's the actual target. So we don't know who it's looking for. And finally, using the key, so it encrypts the actual payload, which is the final goal of the attack, and it completely conceals the malicious intent of the attack. So we see that using this AI-powered targeted attacks can create very, very sophisticated and very precise targeted attacks. And Jiyoung is going to discuss some countermeasures, possible countermeasures for this imminent threat of AI-powered attacks.
Okay. So as you can see, and Dilung explained, the DeepLocker brings a very new challenging problem to our security community. And this is actually the wake-up call to discuss and to think about what kind of possible countermeasures we can develop to protect against this kind of AI-powered attack. And in order to develop a new solution, let's first break down this problem into a small piece. So at the very high level, so DeepLocker actually has 2 main components. First, obviously, it's about concealed payload execution, which is about actual the malicious code. And the second component is about how we conceal the payload and actually the intent using AI. And then let's discuss about, is there any kind of the method or possible countermeasure to address each of the components? So in terms of prevention, so it is highly desirable to have every code running on your system is signed for valid code attestation. And at the same time, if the program, if not necessary, it doesn't have to have the access to all the sensors. For example, if the program doesn't suppose to have the listening the audio or video, it should not have the access to microphone and the camera. And in terms of the monitoring and the detection, now we really need a resilient and powerful the host-based monitoring system. So we have developed a lot of network-based monitoring, but to detect this kind of sophisticated and very targeted attack, we need to catch the moment when the program changes their behavior. For our demo, basically trigger the ransomware. So we need to detect the change of moment of the behavior by monitoring at the host level. And similarly, now we also need to monitoring how the AI use. For example, the outcome about your AI model. For in our case, face detection comes out of generating about all the vector values, and we need to monitoring this vector values how used. For the mobile application, they also have, now these days, they have sophisticated AI model to detect face and maybe changing your appearance, making decorated. They also use AI, but in this case, we are generating key. And there is complete difference. And we need to monitoring AI use to detect this kind of suspicious activities. And obviously, if the key size is small, we can try to brute force, which is an obvious way, but it may not work all the time. And also similarly for the AI. So as the Dylan explained, there is a lot of possible attribute attacker may come up with from the target attribute, but heuristic may help about what kind of class or the attribute they're looking for. So we can maybe get a kind of initial sense, but of course it may not be perfect. And there is a whole lot of the research and then development around the cyber deception. And the cyber deception, the goal is about how to poison the adversary AI model so that they can make a wrong decision. So cyber deception could be one way to address and then parallel execution and then steer the AI to make a different choice so that we can fool the attackers. And lastly, so of course we can try to reverse engineer the payload to understand what is the actual intent of code. And then similarly, for the AI-powered concealment, we can reverse engineer the AI model. Here what we refer is AI lockpicking because we develop AI locksmithing. So basically, AI lockpicking is to answer the question about, so given AI model, what can you learn from it? So in other words, AI lockpicking technique is to derive insight how the internal operation and behavior of AI model. And we want to understand, we need to understand this internal behavior to better protect against AI-powered attack. And of course, from the AI community, there has been a lot of effort to understand and to visualize and interpret how AI model works. So these are the few examples from the recent literature, and for example, the partial occlusion to systematically occlude some of the part of the image to understand which part of pixel is significantly affect about classification result. And in the middle, you can see the monitoring how the neural excitation work for each of the layer and the generating heat map. Again, this is also the goal is similar to understand what pixel of the input image is really significant support the classification result. And also there is another effort about the debugging. So similarly, what we debug our program, the debugging the AI model, is there any error, is there any kind of the disagreement among the different model to understand how the AI model works internally. So for example, using the fuzzing technique, which is one of the recent paper. So all this effort could help understand how the AI model works internally and which can help us have a clue about how we protect and how we prepare the better solutions against the AI-powered attack. To wrap up, so I'm going to hand over to the Mark.
Yeah, so we would like you to take home a few important messages from what we've shown you today. The very first one is really that with AI becoming democratized and being widely available, there are new types of attacks coming our way. We call them AI-powered attacks. And they're an imminent threat to many of our security systems and organizations. There are a number of things that really are going to change in terms of the characteristics of attacks when AI is involved. We see things become really highly evasive. There's a lot of ways of making a new level of scale and speed in the attacks, where reasoning and decision-making can be deeply embedded into these attacks. And there is a whole new form of adaptability and autonomy that these attacks have. Attacks becoming really creative and being able to be extremely surgical and precise when they're executed. Now, what we've shown you today is what we call DeepLocker. This is really just a proof of concept to demonstrate how we can use AI, and everybody can use AI, to craft new variants, mutations of attacks and threats that we're already knowing. But this time, very concealed, very shady, very hidden, and very precise in terms of their execution. But DeepLocker is really only scratching the surface. We haven't explored everything in our research. There are many things that can be done. I mentioned reasoning that can be embedded into the malware to decide when to do what. Let me give you just one example as really summarizing very much, I would say, where this space is heading. Take the DARPA Grand Challenge from 2004, where we had self-driving cars competing in the Mojave Desert to finish a track. Only a few cars actually have completed in the first time, but they got better and better. And look where we are today, 2018. We have self-driving cars. Most of them do a pretty good job. Some of them have some issues still. But we have self-driving cars that can do their job. Now, 2016, we had the DARPA Cyber Grand Challenge, where bots have been fighting each other in capture the flag competition to win. And you can basically extrapolate of what we have seen in these competitions and where the future can be. So I think this is what we have to realize as a security community, as a security industry, that the landscape is yet again to change with AI coming up. So to the last message, and this is really the point, I think our defenses that we have today will become very much obsolete. Think of malware trying to learn what the rules are, trying to circumvent these rules, because these rules can be mined one way or another and can be executed. So we need to come up with new defenses, and we need to study this form of malware, new forms of malware, similar to what we've done with DeepLocker. Think about what can attackers do with AI to find the weaknesses, find the attack points. How can we attack them? Cyber deception, Jiyoung mentioned it before, could be one thing. How can we poison, can we misdirect the attacks, the malware, into believing that they're doing the right thing, but in reality, they're just being pulled out of the real environment and taken down. So with this, I'd like to end, and I'd like to thank you for your attendance. And we're open for any questions you may have. I'm sorry, can you?
Go to the mic.
The size. You want to take that?
All right, I guess we were told not to release too much detail into exactly what we have tested, but maybe we can talk in person.
Yes, please.
It's a great presentation. So when you're talking about object-oriented streaming media or streaming data as it applies to current and existing systems that are already in place, a lot of this would make sense for the sake of data being distributed on a platform where content and subject matter that nobody seems to figure out what the hell is going on when it comes to AI, which still leaves the human capital factor, being able to determine or decipher what exactly it is that they're visualizing. You guys have any thoughts on that area where it applies to what you're saying in conjunction with humans applying this very theory and concept and how it can work together hand in hand?
So let me answer in this way. So the proof of concept implementation that we've shown with the video conferencing application is really just one instance of how you can do this. since any video conferencing application out there is from time to time obviously legitimately using the camera, the DeepLocker malware or concealment can also tap into that camera stream very stealthily and covertly without the user realizing that this application is using video. And from that point, it can start sample pictures and see who is sitting in front of the computer, who is there, can we unlock our malware, and if it does so, yes, it can do so. If other, let's say millions of other people who are also using this very same benign video application, benign looking video application, it will never unlock. And everybody else is thinking this is a good piece of software. It's doing its job, and they will never realize that there is something hidden in there that is only unlocked for one or two or a handful of specific targets it may have.
Thank you.
Mm-hmm. Yes?
So to run the neural network on the target, each time a face passes in front of the camera, what are the computational costs on the target to run something that big, and is it noticeable to the user?
So that's a great question. So there is some computational cost to that. So, but the problem, the attacker may be very, very stealthy. That is, it can only check for maybe, 30 seconds or maybe every minute or something like that to reduce the cost of computation. And the other thing is like there are, if you look at Snapchat or something like that, they're always using this face detection and all these things inside their app. And you can simply embed the DeepLocker type of attack into this kind of model, and it's doing the key generation at the same time it's doing other things. So I think we have systems that is capable of simply handling this kind of computation.
So you can run a neural network on that laptop and not see immense spikes in CPU when that model executes on a face?
So when it's detecting, definitely not. It's not a lot of, it's basically, if you look into the DNN, it's simply you flow through, it's not training, it's actually, putting an image and flowing through the network, and it's not a lot of computation.
Got it. Thank you.
Disable. Thanks.
You guys say this DeepLocker can target many attributes like not only like a picture, audio, software environment, or activities. But as I know, DNN or convolutional network needs specific ranks of input features, but like audio or activities are dynamic lengths of pictures. So is there any way to transform this dynamic lengths of feature to DNN's input features?
So I'm not quite sure I completely understood your question. So are you asking that other than image features, it can also look for other types of feature like network? I heard network.
Okay.
Is that what you're asking?
Yes.
Yeah, I think the possibility is endless, right? So we had a chart. There are different types of attribute that you can use to train the DNN to detect the target, and one of them could be your network structure. You can scan your network, and if you find it's very specific network structure, then you generate the key. That's definitely possible.
Okay, thank you.
Thanks.
Please.
Thank you for your presentation. My question is, how do you reduce your rate of false positive or false negative? Because we know that malware sometimes is difficult to predict or defense, but your AI method is very magic. So I would like to about the false positive or negative rate. How do you reduce that?
Yeah,
So let me repeat the question just so that I understood correctly. So you're asking the false positive detection of the target or false positive detection of the malware?
Malware.
I guess we are not talking about detecting malware. I guess, the DeepLocker is more like what adversary can do to create a malware. So your question is, I don't know.
I mean, I can answer both questions if there are two questions to that. But I think one thing I wanted to say is, if you really think about false positives of the DeepLocker AI to figure out if it's on the right target or not, then this way of what we have seen when we've built and implemented some of the DeepLocker algorithms is that we are building this in a very, very specific way. So very high specificity, almost pretty much zero false positive, wrong identification, because the AI model is so specific that it's only triggering on the real subject. And you can tune this parameter in the model. This is making a lot of sense, in fact, when we're an attacker, because we don't want this malware trigger in the wrong situation. But maybe, as an attacker, we have time, we can wait for some time until we're really sure that we're seeing the attacker in front of us, and only then reveal and release the malicious intent. Now, going to your second question that in terms of how false positives could reveal itself on antivirus system or maybe detection of DeepLocker, we realized this is going to be extremely difficult, because most applications in the future we foresee have some form of AI included. So they're using an AI model and they're feeding something from a sensor or multiple sensors into an AI model. And this is where attackers can try to find their way in and can, for example, take an existing AI model and retrain it. Basically, you can do some form of shallow additional learning to the model itself and add the DeepLocker detector on top of it. So this is also what was called like transfer learning, and it's going to be extremely hard for the detectors to detect similar things. But to be honest, I think we haven't really explored this part in our research, because we really wanted to understand just how AI can be used, and we're not into making this absolutely perfect, but more trying to demonstrate what the art of the possible can be.
Okay, thank you.
Mm-hmm.
Thanks.
Hi. In this scenario, a face detection model or some sort of sensor-based target detection model is based on supervisor learning manner, right?
Let me just repeat. You said supervised learning?
Yeah. So
Yes.
If these models are based upon supervisor learning method, so I think there is a need to correct target data before infection. So are there any way to correct target data or and also train model before correcting target data inside if target machine?
Yes, and absolutely. I think it's a supervised learning process, and it lends itself very well to such a supervised learning process, because we can take Bob here, we can go to his LinkedIn website, we can maybe have access to his Facebook or to his Instagram account, and we can just harvest a bunch of pictures, and we can do a supervised learning and optimize that AI model to really trigger only on Bob. And you've seen we had the faces in the wild, basically, that you can use as the other data set to say, okay, don't trigger on any other face, but really only just on Bob's face. You can harvest faces, millions of faces, of course, from the web, and make this a very, very well-modeled supervised learning model.
I just wanted to add one more thing. So there are two stages, right? The first one is actually capturing the class, which is the face. So you can use different. It doesn't have to be always Bob's face. So you have two stages. First stage, you learn how to understand face, and then the second stage, you understand which face. So you can have always good data for the first phase, and then you only need few data for the second phase.
Okay, I got this. Thank you.
All right.
Hello, very good work. I have a question about key generation part. From my point of view, the key generation, it seems a one-way mapping from the input to the key, and from the key you it's not easy to reverse understand the input, which input you are targeting, right? So this property is quite similar to the hash function.
Exactly.
Yes. So any comments about, say, if that possible, I using Hashi function to replace the key generation part? What's the pros and cons?
Yeah, that's a great, so actually that's how we started. Our thought process was basically, you can actually hash the key. For example, in case with Stuxnet, instead of putting the entire value, it could actually hash what it's looking for, and then you will never know. But this kind of hashing only works for very deterministic targets, right? If your attribute is very, very deterministic. But what we're talking here is very high-level concept like face, and when you detect those things, as I mentioned earlier, the key would be not stable. There will be some bit flips, and it's not going to work exactly the way, because like what would you hash, right? So you generate maybe some feature vector for your facial feature, but if you hash that, it's never going to be the same hash. So I hope that makes sense.
Okay, so from your point of view, it seems the AI based is tolerant some the noisy, right?
Exactly.
It's more
Yeah.
robust for the some comments. Okay, thank you.
Thank you.
All right. Thank you very much.
One more question? Or
out of time.
Oh, we're good. Sorry.
Just a quick follow-up from the guy who asked about the CPU load earlier. So I might have missed this earlier, but at the point where Bob's face was recognized, that means his images through the camera were being somehow exfiltrated by the network into the DNN, the AI part of the network, right? And that is when the key was matching weights or key were generated, and then the key was matching on the terminal. Is that right?
So there is no network activity in there. Oh. So everything is in the application itself. The neural network is this construct that is deeply embedded in the application itself, and the face, the picture, the pixels are basically sent to that local network component. You can look at it as an API call, and then you get back a result of what the neural network thinks it is, or what are the outputs.
Okay, so sorry, quick follow-up. So how is it? Obviously, that needs some kind of computation to to match that, right? So isn't that gonna generate some kind of CPU spike, heat, and all that?
Not in our experience. I think neural networks these days are very powerful. Also, their implementation is very powerful, and you have a lot of neural nets or AI already running perhaps in applications, so it's very hard to distinguish them from legitimate use of AI. As mentioned before, we can piggyback also just on regular AI models and embed some of the malicious output in legitimate models. That's definitely realistic to think about.
Okay. Thank you so much.
Thanks.
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 All right.